Okay, so what we had said about physics was pretty much where it sat among the other sciences and what it studies. It studies basic things, meaning things underlying everything else. And we've listed a few examples here: energy, heat, light, and electricity. Can anyone give me a few more examples of things you've heard of as something being studied in physics?
Just the study of motion in general.
Yeah, that's a big part, actually. So, in the physics sequence, if you are in the life sciences or you're in engineering or physics, your whole first class is pretty much the study of motion. Okay, if I need to move something, what has to happen? What has to act on that thing to make it move?
Work.
Force.
Yeah, a force. Work I'll lump in with energy. So they kind of form this pair of work as an exchange, energy is the result. Um, what else?
Sound.
Yeah, let's go ahead and fill in the rest. So just a general study of matter, and more specifically, atomic structure and magnetism. And you could list plenty of others, but they start to get into more niche areas of physics, so we'll just leave it at that. These are things that you could talk about in really any field of science in some way or another, even medicine, physiology, that sort of thing. So, understanding physics helps you understand other sciences and just better understand the way the world works. We could even say explicitly how chemistry and biology build off it. So, chemistry studies how atoms combine to form the molecules making up matter. So that is building on top of physics' view of atomic structure, which is the area of quantum mechanics, mainly in physics. And so there's quite a bit of complicated math in there, but it just studies the motion of electrons and bonding between atoms and all these things happening at this scale that we're just not used to seeing every day. Biology builds on that by looking at specifically how molecules combine to make life. And so each has kind of a different tool set and a different level of abstraction to talk about these things. Physics gets the most deep in the weeds, and because of that, it makes you spend kind of the most time on one specific area. And that's why I think physicists have a reputation of being these really neurotic people, because they are. We like to look very closely at things and spend a lot of time on them. And that's not always the best way to go about things, but it is a way to get a really deep understanding of them. Chemistry sits under biology because it's the study of matter generically, and then physics underlies that because it gets more specifically into what is matter. Scientific methods really isn't as important as middle and high school classes would make you think. It's one way of getting to a result. It's really not this way that everyone sits down and decides to do. I don't even make you write these because it's one structure that some scientists sometimes follow. And it's you come up with something you want an answer to, you make a guess on it, you predict what that guess says, you then do some experiments to verify or disprove your guess. And then if it supports your guess, you come up with a rule to explain all of that. If it doesn't support your guess, you just kind of restart the whole process. More often, what happens is people just kind of go their own way with this. They have some things that maybe work of how they do their work, but it's not as structured. Some people even just do some drugs and sit down and have an idea. That's actually happened more often than you'd think in a lot of sciences. For instance, supposedly the structure of DNA was discovered while Watson and Crick were on LSD, even though really the discovery should have been credited to, I believe it was Rosalind Franklin, a woman. But these two guys came along with a similar idea a little bit later and get most of the credit. Some discoveries just happen kind of purely by accident or purely by not scientific means. As long as the science holds up at the end, it's all right. It's more important to just have a good attitude about science. And so that means having a few qualities. So inquiry, maybe that one's obvious. What does that mean? What is an inquiring mind?
You question a lot.
Yeah, to the point that you're maybe a little bit annoying. You were that kid who just kept asking your parents why until they got frustrated. That would make you a great scientist. So, curiosity about how the world works. What about integrity? What does that one mean?
The honesty in one's work.
Yeah, you want to make sure that you are not the most important thing in the world when it comes to your work. So, if, for instance, you've been working on this project for years, and it's based on some hypothesis you've had, and you come to find out that original hypothesis was wrong. And that means a lot of your work is kind of a dead end that you went down for years. It's your responsibility to still let everyone know that, even though it may make you personally look a little bit worse. And that's actually a big problem in some of the sciences now, is that people have gone very far down these roads and not told anyone. And the only way anyone figured it out was by looking more closely at their data, trying to recreate their experiments and not having the same luck. And so it just leads you down this path of, if you want to maintain that view of things, you kind of have to start making up data, kind of fudging your results a little bit. So it's putting science above yourself. So this is another one that's kind of a problem in modern academia, is you may have heard of the publish or perish mentality, which is the idea that you want to get out as many papers as possible to kind of fill out your CV, which is like your resume, just an extended version, a curriculum vitae. And so what you do is you just put out little papers that have a little bit of your results at a time. And eventually you have maybe 10 tiny papers that could have been 2 or 3 really good large papers. And that looks better on a CV. Okay, so what's the downside to that?
People are getting their information like very late, and if somebody is trying to recreate it and like get it from you, you putting it slowly out. People
Yeah,
might get interested in it.
yeah, and it's you're exactly right. You just don't get the same access to information, and it's not as useful to others. And so it's really not serving the purpose of a scientific paper, of letting everyone else know what you found in your area of study. And it's an even bigger problem when you consider that a lot of times, unless you have some connection with the publishing house that the paper is published through, like the journal that it's published through, you're paying $35 to $50 per paper. And it usually does not depend on the length of the paper. It just depends on the journal it was published in. So you could publish 10 articles at $35 a pop, or you could publish 2 at $35 a pop. And so, even money wise, it's not the most ethical thing to do for others. Humility. So, what does that mean?
Being able to acknowledge when you're wrong.
Yeah. So, maybe you and a lot of others even have this idea about some area of physics that's still not very well understood, like black holes or quantum gravity, all these things of like, how does gravity work at the small scale? And there are a lot of different ideas. But say someone comes up with some experimental findings that knock a lot of those possibilities out, meaning the different theories are not supported by that experiment. Well, those people who were supporting those areas, those theories, should not continue looking into them, because it is not the way that the world actually works, apparently. But that's not always how it works. A bunch of people will continue and post even more and more abstract papers studying this thing in more and more detail until someone says, "Why are you still doing this?" There's no actual scientific value here anymore. And it's because it's human nature to not want to just drop something you've spent years working on. So it's an unfortunate side effect of being human that doesn't always mesh with science is you don't want to be wrong, but in science you have to do that. And another thing is the whole population has for a long time thought some wrong things about the way the world works. We'll see that with Aristotle and the people following him. That was a big time of maybe a lack of humility in places. In the 1900s, there was something called the ether theory, which was how we thought that light moved through space. And most everyone thought that was how it works until an experiment disproved it. And some people tried to interpret that experiment as actually proof that things traveled through the ether, just because they didn't want to let go of that idea. So, humility is acknowledging errors or misunderstandings you may have about the way things work. And like with the ether theory thing, adapting to new findings. So dropping whatever the old thought was on things if it's not supported by experiment. I think the one that has probably the most issues nowadays is academic integrity. You can find so many cases of people falsifying data, and apparently it's kind of a crisis in psychology right now of so many studies that cannot be reproduced because the data was just so kind of either misinterpreted statistically or just fully made up. So it's something that we got to be more and more careful about nowadays of actually checking what we're reading and if it makes any sense. Okay, so we're going to talk about a few terms in science that sometimes differ from their everyday usage, and that can lead to misunderstandings, especially in like news articles that are written by non-scientists. If it's like pop science, you can see a lot of things that really aren't what's actually happening in the research, but it sounds flashy. And part of it is misunderstanding of scientific terms like these. Okay, so the first one is a scientific fact. It's actually a looser sense of a fact than what we think of in everyday speak. It is this kind of long-winded phrase, a close agreement by competent observers who make a series of observations about the same phenomenon. That's just saying, okay, we don't know the way the world actually works. We never really will unless someone hands us a rule book for how it all works. We're just kind of guessing what's behind the curtain as best we can. And we can get pretty good at that. You know, you shine a light at the curtain, that tells you something about it. You play a sound near the curtain, that tells you something about it. But eventually, you're only going to get so much detail without being able to open the curtain. And as far as we know, we can't do that and see what's going on behind the scenes. So, facts can change a lot in science because they're just our best guess at the moment. They're what everyone agrees on as of right now. So we'll see how facts can change in science. Hypotheses are going to be our big one for the chapter because we're going to be distinguishing between good and bad, or probably better to say scientific and non-scientific hypotheses. A hypothesis is an educated guess only presumed factual until supported by experiment. So presumed factual means it's just what you're running with, what you're working with, until you have an experiment to back it up. It's your initial guess at something, and until it has any validation, it just remains a hypothesis. Eventually, it could be developed into a scientific principle if it gets more backing, and then it can be enveloped up into part of a scientific theory, which we'll get to in a minute. So what's more important is a scientific hypothesis. And that means one you can actually do something with. You can test it. And what we mean by testable is, and this is maybe going to sound a little odd, we want a test that could, in principle, prove the hypothesis wrong. So why would we want a test that can prove our hypothesis wrong if our hope is that our hypothesis is right?
Because if the tests you run on your hypothesis being wrong come back negative, it supports your claim.
Yeah.
It'll lead you to, I guess, being able to research like what the true hypothesis would be.
Yeah. So if the test fails, then it supports your claim, like you said. It's saying, okay, we tried something that should disprove this thing, and that thing turned out to be wrong. So our hypothesis is still holding up for the moment. So that's one good thing about it. The other thing is that something being right really isn't all that powerful as far as scientific understanding goes. You may, just under the specific circumstances of the test you did, of the experiment, get something that supports your hypothesis. But someone could do a similar experiment that they just happen to do in a different part of the world, or with the lights off versus on, or any variant of things, just some slight change, and somehow your hypothesis is no longer supported. So something being right is kind of a fragile thing and not all that telling of the underlying hypothesis. It just tells you about what that hypothesis says or how right it is in the one specific circumstance you tested it under. So my kind of analogy here is even a broken clock is right twice a day. Right? If it's broken, it's sitting on 5 o'clock, it's going to be 5 o'clock 2 times a day. So if you happen to look at the clock at those 2 times, you're going to be like, huh, the clock's working. Same with a hypothesis. If you happen to test it under very specific circumstances and it works, you're like, huh, it's working. But in reality, it may be completely wrong in every other case. But if your clock is broken, then you know pretty quickly. Every time you look at it, you're like, huh, it still says 5 o'clock, but it's not 5 o'clock anymore. So if a clock is wrong, we know it's flawed. And so we can quickly update, we can fix the clock up a little bit and then try again. So something being wrong is a more powerful concept than it being right, and it allows for quicker progress. That's not to say we want our hypothesis to be wrong. We just want it to be tested for wrongness many, many times and hopefully pass all of those tests. And then we start to say, after passing many tests, huh, maybe it is right as far as we know. Okay, so let's try and practice with a few hypotheses and decide if they're scientific or not. So how you do this is you read the statement, you think of a test that could prove it wrong, and if that test is something reasonable that we could do, then it is a testable hypothesis. So I'll do the first one, and then you can try the second one. So atoms are the smallest particles of matter that exist. I come along and I say, I don't think so. I think that's wrong, and I'm going to test that. How can I test to see if this statement is wrong? Well, if it were wrong, that would mean that there are particles smaller than atoms that exist. And so to test for that, I search for smaller particles. That sounds like a test that I could possibly perform. And so the hypothesis is scientific. Okay, so even if I didn't find any smaller particles, that would be actually in support of this hypothesis. But it was still something I tested for. It was something I was able to test. And that's what's important here for a hypothesis being scientific. We actually know that there are smaller particles than atoms. There's protons, there's neutrons, those are made up of quarks. So this is definitely not a true statement, but it is scientific. So even though this statement is not true, it's still scientific. Okay, so I want you to try part B. Okay, so what are our thoughts on this one?
I think no, because if you do try to think of it as a wrong thing, you will try to go in going into space and trying to detect things that you see that's out there. But how would you know that you're not detecting other essences?
Yeah, so it's this thing of undetectable. That's really the key word. Is if it's undetectable, how could we test for it one way or another that it is there or that it isn't? So it's like we'll talk about in a little bit like ghost hunting. Even if ghosts exist, we don't have any test that really tells us anything about that one way or another. And so it's not a testable thing. So that's the problem here. Um, not scientific. If the essence is undetectable, there's no way to test for its existence. Or non-existence. So really you can't figure out anything about it. Maybe space is filled with this undetectable essence, but we have absolutely no way of knowing because of its undetectable nature. And that is, you start to run into some areas of physics where it's is really towing that line. String theory is one of it's the idea that the smallest particles of matter are not really particles, but these vibrating strings that somehow combine to form the matter we see. If they're that small, it gets to a point where it's like, how do we really test to see if that's what's there? But I guess they've found ways to look for those things. Although the ongoing issue is that there's no experimental evidence for string theory. And so it's becoming sort of a niche, a more and more niche area of physics. Okay, hopefully this one's pretty easy. Albert Einstein was the greatest physicist of the 20th century. Is that scientific or not?
No, that's opinion. That's it. It's not scientific.
Yeah, so opinions generally are not. If it's these sort of qualifying things, especially about people or whatever else. So the biggest issue, if we really try to break it down, is greatest. What does that even mean? It's not specific enough to have a test that could disprove it. So, I may come along and say, I don't think this is true. I think there's a better physicist from the 20th century. But what is my test for that? I have to come up with what greatest meant in the first place. And so it's not even specific enough to be testable. So, not scientific. There isn't a test. To determine if this is true or false. Now, I could revise it to something like Albert Einstein had the most cited publications of the 20th century. That's something testable. I just have to go in and look and see if there were any scientists whose publications got more citations in the 20th century. So that's a very doable thing. And so that would be a testable and so scientific hypothesis. But greatest is just not specific enough to warrant a test or to be able to come up with a test. So now we're going to ask two very similar but slightly different questions. And this one is tricky, okay? This one trips up everyone on the first time. So here, you want to think about that idea of coming up with a test that could prove it wrong, and then decide if that test is something we could ever actually do. Like, as a human species, is this a possible test? Okay, so look at these two options. Alien life exists on other planets, and alien life does not exist on other planets. Decide which is scientific and which is not. What do we think? Who thinks A is scientific? Who thinks B is scientific?
I think A is scientific.
Okay, let's get a few more thoughts, and then we'll start thinking about why.
I agree. I think A is scientific.
Okay, any others feel B?
A would be a lot easier to check to test.
Okay,
Wouldn't B be more of like an opinion? Because the word alien means it's like not from Earth. So if you say that it's not alien, it doesn't make sense.
so let's say just intelligent life, just something living on other planets. It's not meant to be a red herring. All right, so no votes for B. All right, why do we think A is scientific?
I said A because when we was just talking, you have to be able to somewhat prove it wrong.
Mhm.
If we are able to prove it wrong, it has some validity that we can go to other planets, see if there will be able to even support human life, if it could support another life.
Okay. Um, let's do it this way. Let's come up with what it would mean for A and B to be wrong. We'll start with that. So, what would it mean if A were wrong? It would be wrong if,
other planets cannot support life at all.
yeah, so if there's no life on any other planet. Okay. And for B,
We actually find something?
yeah. So life exists on some other planet. Doesn't have to be every planet, but we just find it somewhere. Okay. So you come along, you're the contrarian saying, I want to test this, see if it's wrong. What would your test for wrongness be? In either case. So for A, what would your test to try and prove that wrong be?
You'd probably have to observe every single speck of terrain on each other planet.
There you go. You have to check absolutely everywhere if you want to say that there's no life anywhere. So to test for wrongness, every planet in the universe for life. Okay. What about for part B?
You would just have to find one instance of life
Yeah.
anywhere.
Check until you find life. Now, if there truly is no life on any other planets, if this hypothesis is correct, you will really have to check every single planet. but it's not required at the outset like it is in part A. So check until you find life. So this could, in principle, take you a very long time, and it has for us, but it's not absolutely guaranteed that it's going to take you a very long time like it is for part A. Because in part A, you have to check every single planet in the universe. There's no way around it to try and disprove that hypothesis. What does that say about whether A is scientific or not scientific?
It has to be reasonable, so it wouldn't be reasonable for you to check every single planet to test if aliens exist or not.
Great. So it's not scientific because it's not reasonable. But is the test... Yes, go ahead.
How isn't it reasonable? Because
So, okay, I task you with this. I tell you, I want you to test for this and perform this test for wrongness. I want you to go to every planet in the universe, scour its entire surface, and tell me if you find life. Do you see that you don't want to do that?
yeah, I do.
Yeah. Yeah, so that's really it is a test that you could perform. It's there. It's not like some of these others where there just isn't a test. It is a test. It's just not one that anyone in their right mind ever wants to do or is worth doing because it would take, as far as we know, forever because we don't even know exactly how many planets there are or how much surface area we'd have to cover to test for this. But for B, in principle, you don't have to look at every planet. You just have to look at enough to find life. The only way you would have to look at every planet is if the hypothesis were correct, meaning alien life doesn't exist anywhere. So that's what I mean about you get wrapped up in all these double negatives and weird logic things. But that's why it's good to break it down into what would it mean for it to be wrong? How would you test for that? And is that a test you can perform? So in this case, B is actually the one that is scientific. And it feels weird because we're constantly searching for life on other planets. But the way that that's being kind of done, I guess, on the back end is testing to see that there isn't any life on other planets. Questions so far? Okay, then let's talk about a couple other kind of terms we use in science that don't always mesh with everyday life. So a law or principle is a hypothesis that, for one, was testable, and two, has been tested many, many times without anyone coming up and saying, aha, I did this test, it proved the hypothesis wrong. So it's that thing of you can never truly prove a hypothesis right in the sense of there's no arguing with it whatsoever, but you can test for wrongness many, many, many times until you're like, guys, we've tried everything in the book and this thing still holds up. It's looking pretty good. That's when you promote it to a scientific law or principle. Same thing. Okay, so an example of that would be Newton's laws of motion. So in their area of validity, and by that I mean you're dealing with everyday masses, everyday speeds, Newton's laws seem to apply very, very well. So they describe the motion of objects in terms of the forces acting on them. And we'll talk a lot more about Newton's laws later. Okay, so you test a hypothesis many times, it gets promoted to a law or principle of science. You bring together several of those that are related to each other, and you have yourself a theory. So It's some synthesis of information that's combining multiple ideas into a more complete description of some area of science. So cellular theory, the idea that things are made of cells, the atomic theory that on an even smaller scale things are made of atoms. Those are theories that have lots of little principles building them up. We will talk more about the theory of classical mechanics. That is explaining the motion of objects using Newton's laws and a few other principles. Those other principles that we'll talk about more later are conservation of energy, conservation of momentum, and a few other things here and there. But like we said about facts, none of this is set in stone. All of it is subject to change if we find a better description. And so we got to be a little bit loose on all of them, and that's really the big difference with everyday language. We think of facts as fixed ideas. We think of a law or a principle as a very fixed thing. And weirdly, we think of theories as less kind of set in stone than a law, even though it's a building up of laws and things. So we think of it like it's a hypothesis in everyday language, but a theory is actually a more powerful statement. It's a more tested idea than a hypothesis is. So a couple examples of where these things have had to change. We used to think the universe was static, meaning where galaxies and things sat relative to each other was pretty fixed. Now we know that the universe is in fact expanding. Everything's getting farther away from everything else. So when we had information from, for instance, the Hubble Space Telescope and earlier observations that started to say things are getting farther apart from each other, we had to drop that idea that the universe was static. And even Einstein thought that. He did not include a certain what's called cosmological constant in a famous equation of his until later because of that mounting evidence. And I think he's quoted as saying that was one of the biggest mistakes of his life. Okay, classical mechanics, that one I just said, is this theory of motion. It's really a theory of motion in specific cases. And so in other cases, it doesn't work and we have to switch to other theories. So if we're talking about very small things, we have to use a different theory. Things like atoms and electrons. And that theory we have to switch to from classical mechanics is quantum mechanics. If we're talking about very fast things, meaning light, some other massless particles like neutrinos, there's a different theory we use. It's called special relativity. So you may have heard of relativity as this, it's usually treated almost mystically in pop culture, but it's just a better description of motion when things are moving very fast. That's all it is. If we're talking about very massive objects being present, things that have a lot of mass, so galaxies, and even smaller things like stars, planets, this can be relevant. We talk about general relativity. So it's an improvement on special relativity for when mass is present in the space you're talking about. And you could combine these and talk about very small, very fast things. That's quantum field theory. Very massive, very small things. That's quantum gravity, and so on and so forth. And so there is some theory out there that combines everything, gets it all as right as possible, and that's what's, I guess, called the grand unified theory of physics that we've been searching for, I guess, all of human history. Anything in science is subject to change, even these things we'll talk about in the class. It may be 200 years down the road, someone's going to say, even that's not quite correct in everyday life. So we just kind of have to put up with that. But it is not a bad thing. It is actually a very, very important thing to continue updating, continue just accepting that we're wrong and we need to do better, because if we don't, bad things happen. So here's one bad thing. We could actually say Aristotle is, unfortunately, one of the biggest hindrances to early physics of any human being in history. So he said a lot of things, didn't check really any of them, and people bought it for a very long time. So one of the things he said was that if you drop things, they fall at speeds proportional to their weight. All that means is if you've got two things, one of them is twice as heavy as the other, it will fall twice as fast. We hopefully know nowadays that's not true. And the first person to contradict that statement and say that is not the case is Galileo. And really, he's the first person to test it and demonstrate to everyone that that is not a true statement. Instead, he found that things fall at pretty much equal speeds. We're going to do basically the test Galileo performed right now. So this is the easiest demo of the entire semester. And because of the snow, I went into U of M to record a bunch of demos for different classes yesterday. This is one of them. All right, so we're going to disprove Aristotle's claim and support Galileo's right here. We are going to perform a very simple experiment that wasn't attempted for most of human history. We have a tiny notepad and a large folder. The folder weighs about 5 times as much as the notepad. I'm going to drop them both at the same time, and we're going to see which one hits the ground first. Make your predictions. 3, 2, 1. Okay. It is the simplest experiment you can do. And yet apparently no one did it when Aristotle made that claim for a very long time. How much longer do you think it took after Aristotle made that claim for it to be disproven by Galileo?
Well, I mean, I can get why it took so long because they probably like grabbed like a feather and like a stone
And
and
you're
dropped them.
right on that that is kind of a exception. And we'll talk about why that's an exception. But even then, it's not a direct proportionality. So it wouldn't fully agree with Aristotle's, but you're right that it doesn't fully agree with Galileo's. And we'll talk about Galileo's full statement a little bit later. But even like dropping a pebble and a rock, no one apparently did for a while after Aristotle.
500 years?
100 years? It's a good guess. Almost 2,000 years. 2,000 years. So you can see why this is a problem of this most basic experiment that could be performed was not attempted for almost 2,000 years. It's something like 1,600 years. It's not that everyone just didn't bother to test it just because. It was because they said, well, it's Aristotle. He's one of the most famous philosophers of our time. How could he be wrong? And so they just went with it. And then the people that came after them said, well, our ancestors said, or our parents said, this is the case. And they said it's because of Aristotle, and so on and so forth for apparently almost 2,000 years. So that was the issue. No one questioned Aristotle's authority. That's a big thing. Science shouldn't allow appeals to authority. Because it has no factual basis, no experimental basis. It's really just that this guy is the smartest guy in the room, supposedly. Even things that Einstein has said, we talk about Einstein all the time, almost like he's a god of physics or something. But it's just because the statements he made have passed the tests of many different experiments. And so that's why he is kind of revered in physics, is because his ideas were correct as best we know, not because he was just this really, really smart guy. So we're not really appealing to the authority of him when we talk about him. We're just appealing to the correctness of his ideas and the creativeness of them, because they are pretty out there when you start to think about what he's saying. And that's that relativity stuff we just discussed. Okay, so that's a good place to stop for today. We should finish up this set of notes next class, meaning we'll start the next chapter after that. I guess given the circumstances, we'll probably skip the first quiz, or maybe I'll make it online. We'll see. But I will get the second set of notes posted by tomorrow so that you can have them for Wednesday. Are there any questions before we call it a day today? All right. Well, I will see you all Wednesday then. Stay warm. Have a good day.
You too,
Very well.
sir.
Thank you.